The Mississippi River drains 41% of the continental United States. 41%. Every raindrop that falls on the eastern slope of the Rockies, every snowmelt running down from the Appalachians, every flooding creek from Montana to Pennsylvania, all of it moves toward Louisiana and exits through a single delta into the Gulf of Mexico. The port system at the mouth of that river moves more tonnage annually than any port complex in the Western Hemisphere. By every law of geography, every calculation of strategic advantage, Louisiana should be the most powerful and prosperous state in the nation. It ranks 49th in education, 50th in opportunity. No other state in American history has sat on a geographic inheritance of this magnitude and delivered so little of it to its own people. That is not an accident. That is a story 7,000 years in the making, and it begins not with politics or poverty, but with the ground itself. Subscribe now, or lose the thread. The algorithm buries this kind of content. Pin it down. By the end of this video, you will understand 3 things that most Americans, even those who grew up within a day's drive of the river, have never been told in the same room. You will understand why Louisiana's land is physically disappearing today at a measurable, documented rate, losing in a single day ground that took millennia to build. You will understand why the federal government is currently spending hundreds of millions of dollars to prevent a river from doing what rivers naturally do. And what would happen to the American economy if that effort ever failed? And you will understand how a political culture forged in the 1930s is still suppressing this state's ability to build anything permanent nearly a century later. The textbooks treat Louisiana's problems as a sequence of disasters: Katrina oil spills, floods, but when you examine the geology beneath those disasters, a different picture emerges. Every crisis, Louisiana has faced traces back to the same foundation. A state built politically and literally on ground that was never designed to hold weight. Before we reach the politics, the oil money or tea floating, we need to start with what Louisiana is made of, because that answer changes everything that follows. Louisiana has no bedrock. Beneath its highways, its refineries, its centuries-old buildings, there is nothing but compressed river sediment, stacked in some places over 1,000 feet deep. That is not a geological curiosity. That is the foundational physical fact that explains every crisis this state has ever faced. To understand how that happened, you need to understand what a river delta actually is. The Mississippi carries roughly 500 million tons of sediment every year. Soil eroded from farms in Iowa, silt scraped from riverbeds in Illinois, fine clay suspended in floodwaters from across the interior of the continent. When that sediment reaches still water, it drops. It has been dropping in the same general area at the bottom of Louisiana for approximately 7,000 years. What you are looking at, when you look at a map of Louisiana, is not land in any traditional geologic sense. It is an accumulation. A deposit, the way a sandbar forms downstream of a rock in a stream, except on a continental scale, built over millennia. Stop and translate that into physical reality. The bedrock beneath Manhattan sits roughly 20 feet below street level in New Orleans. You would drill through 1,000 feet of river mud before striking anything solid. Te entides siti its foundations, its drainage infrastructure, its oldest buildings, rests on material that was submerged within recorded human history. This process of delta construction is not random. The Mississippi does not build one continuous landmass. It builds in lobes. For roughly 1,000 years, the river establishes a primary channel and deposits sediment at its mouth, extending a new finger of land into the Gulf. Then the river finds a shorter, steeper path to the sea, shifts its course, and begins building a new lobe somewhere else. The old lobe, cut off from its sediment supply, begins to sink and erode. Geologists call this process delta switching, and the Mississippi has repeated it at least 7 times in the last 7,000 years. The current lobe, the one we call Louisiana, is not the end state of this process. It is the latest chapter in a sequence that has not stopped. The United States Geological Survey has measured what happens when that natural sediment delivery is interrupted. Since 1930, Louisiana has lost approximately 2,000 square miles of coastal land, an area roughly the size of the state of Delaware. In the most vulnerable zones, land is disappearing at a rate that engineers translate into football fields to make it comprehensible one every 100 minutes, on average, without pause. The answer turned out to be both simpler and more alarming than expected. Louisiana is not sinking because of any single catastrophe. It is sinking because the process that built it has been deliberately interrupted. But that discovery raises an even larger question. Who interrupted it, and why? The Mississippi River has been trying to change course since at least 1950, and by every hydrological calculation, it should have already succeeded. Here is the mechanism. Approximately 300 miles north of New Orleans, near a small town called Simsport, a tributary called the Atchafalaya River branches off from the main stem of the Mississippi. The Atchafalaya runs almost due south and reaches the Gulf of Mexico in roughly 140 miles. The Mississippi's current route through New Orleans covers nearly 340 miles. From the river's perspective, from the perspective of gravity and hydraulics, the Atchafalaya is simply more efficient, shorter, steeper, less resistance. Every year, the Atchafalaya draws slightly more of the Mississippi's flow, pulling the river incrementally toward the shorter path. By the early 1950s, hydrologists at the Army Corps of Engineers calculated that, without intervention, the Atchafalaya would capture the full river somewhere between 1970 and 1990. Not gradually. Rivers do not shift gradually. They reach a hydraulic tipping point and then divert in a matter of years. When that happened, New Orleans and Baton Rouge would be left on a slow, silting backwater. The ports, the refineries, the municipal water systems, all of it, designed around river access, would become economically stranded almost overnight. Stop and translate that into physical reality. New Orleans sits within one of the 12 largest port complexes in the world by cargo volume. The river channel it depends on carries roughly 500 million tons of freight annually. The agricultural output of America's interior, corn from Iowa, soybeans from Illinois, wheat from Kansas, reaches international markets through this single corridor. If the river moves, that corridor moves with it. The disruption would not be measured in billions. It would require restructuring the entire American agricultural export economy. This vulnerability was not accidental. It was designed in from the beginning. When French colonial engineer Jean-Baptiste Lemoyne de Bienville chose the site for New Orleans in 1718, he was making a pragmatic decision against the advice of nearly everyone around him. The location sat on the highest available ground in the delta, a natural levee slightly elevated above the surrounding swamp. Slightly is the operative word. The levee rose perhaps 8 feet above the surrounding terrain. Bienville's superiors called it a mistake. One engineer described the site as impossible. Bienville built there anyway, because the natural levee was the only ground in the delta that could support permanent construction without constant flooding. What made the site workable barely was enslaved labor. The first levees that protected New Orleans were built by enslaved Africans between 1718 and the 1740s, under conditions that proved fatal to a significant portion of those performing the work. The colonial city's infrastructure, its drainage ditch, its flood barriers, its first roads, was constructed through forced labor on ground that required continuous intervention simply to remain above water. The relationship between Louisiana and its landscape was extractive from its first decade. The land demanded constant management. Management required a captive workforce. When that workforce was eventually freed, the infrastructure remained, along with the political and economic assumptions embedded in how it had always been maintained. The Atchafalaya diversion problem and the colonial engineering problem share the same root. Both reflect a founding decision to build permanence in a place that actively resisted it, and to defer the cost of that resistance to someone else. What came next was an attempt to lock all of this in place permanently. New Orleans is not merely at risk of flooding. It is already below sea level, and the engineering project built to protect it is the primary mechanical cause of why it continues to sink. To understand this, you need to understand what New Orleans was before it was drained for most of the city's first 2 centuries. The land between the natural levee and Lake Pontchartrain, roughly 2/3 of the city's current footprint, was swamp. Not swamp adjacent to the city. Swamp. That was the city. The neighborhoods that flooded catastrophically during Hurricane Katrina, the lower 9th Ward. Lakeview, Gentilly, did not exist as dry land until the early 20th century. They were wetland, seasonally flooded, ecologically active, until a New Orleans engineer named Baldwin would invented a series of large-scale pumps, powerful enough to drain them. Beginning in the drainage was celebrated as a triumph of engineering. Consider what it actually set in motion. The swamp soil of Louisiana is composed primarily of organic matter, decomposed vegetation, compressed plant material, the biological accumulation of millennia of wetland ecology. When that material is exposed to air, when the water is drained away and oxygen reaches the soil, it begins to oxidize. It compacts. It shrinks. It literally disappears. The process is called oxidative subsidence, and it is irreversible. Once organic sediment has been drained and compressed, you cannot restore its volume by reflooding it. The bowl-shaped depression that filled with water during Hurricane Katrina in 2005 was not a natural feature of the Louisiana landscape. It was engineered into existence over 90 years of drainage. Every year, the pumping system ran, keeping the city dry, enabling development. The land beneath those neighborhoods compacted further. Parts of the lower 9th Ward are now 9 feet below sea level. The ground is still sinking, still compacting, at roughly 1 to 2 inches per year in the most affected areas. According to measurements from NASA's Jet Propulsion Laboratory, the irony here is precise, and it is worth holding for a moment. Before the modern levee system hardened the Mississippi's banks, the river overflowed every spring. Those floods were destructive by any human measure, and they were also the mechanism by which the river replenished the delta, depositing fresh sediment across the coastal plain, continuously replacing what compaction and erosion were removing. The levees stopped the flooding. They also stopped the replenishment. 7,000 years of natural delta maintenance ended in a generation of concrete construction. What you have in New Orleans is a system locked in escalating commitment. The city is below sea level because it was drained. It must be pumped continuously to remain habitable. The pumping accelerates the deeper it sinks, the more powerful the infrastructure required, simply to maintain a status quo that is itself deteriorating. The Army Corps of Engineers estimated the post-Katrina flood protection system at approximately $14 billion. That system does not solve the subsidence problem. It delays the consequences of it. Louisiana built a city on sediment, then built an economy on that city, then spent a century building an engineering apparatus to prevent the sediment from behaving like sediment. But the most unsettling part is still ahead, because the physical trap Louisiana built for itself was matched, layer by layer, by a political trap constructed at exactly the same time. Huey Long died in 1935, but the political architecture he built still determines how money flows in Louisiana today. Long's legacy is genuinely complicated, and that complexity is precisely what has made it so durable. As governor and then senator through the late 1920s and early 1930s, he built roads where there were none, constructed a modern state university system, provided free textbooks to poor children, and broke Standard Oil's monopoly through direct taxation. These were real achievements, delivered to a population that its previous government had effectively abandoned. The historical record presents Long as a populist demagogue, every man a king, the Louisiana strongman. That version is not wrong. It is incomplete. What Long also built was a transaction machine. Political loyalty required payment. Contracts, appointed permits, all of it moved through a network of obligation that made the boundary between governance and extraction permanently porous. When Long was assassinated in 1935, the machine did not collapse. It was inherited, adapted, and institutionalized. Louisiana consistently ranks among the highest states in the nation for public corruption convictions per capita. That is not a flaw of character. It is a structural inheritance. What does it mean when a state's most valuable natural resource becomes the primary vehicle through which that corruption operates? The oil boom answered that question in concrete terms. Louisiana's offshore and onshore petroleum reserves made it for several decades in the mid-20th century one of the wealthiest states in the Union on a per capita resource basis. The revenue from extraction was enormous. The investment in durable institutions was not. Oil and gas money funded state budgets, which funded patronage networks, which sustained political machines that had no incentive to diversify the economy. because diversification would reduce the value of the permits and licenses that kept the transaction system operational. The physical consequence of that arrangement is visible from satellite imagery along the 85-mile stretch of the Mississippi between Baton Rouge and New Orleans. Approximately 150 petrochemical facilities, refineries, chemical plants, plastics manufacturers are concentrated in a corridor that researchers began calling Cancer Alley in the 1980s. The communities living in that corridor, predominantly low-income and predominantly African American, face some of the highest rates of industrial air pollution exposure in the United States. The economic value generated by those plants flows primarily outward to corporate shareholders and state tax revenues. The health burden stays local. What left Louisiana was the workforce that might have built something different. Every cycle of the oil economy that enriched the extraction sector and in education contributed to a persistent brain drain. The steady departure of educated workers towards states with more diversified, more dynamic economies. The physical infrastructure of Louisiana sank beneath sea level. The human capital infrastructure followed the same trajectory. The old river control structure does not look like what it is. From there, it appears to be a modest arrangement of concrete gates and steel mechanisms stretched across a few hundred yards of Louisiana wetland, roughly 30 miles south of Alexandria. What it represents is the most consequential piece of water infrastructure in the Western Hemisphere, the mechanism that prevents the Mississippi River from becoming the Atchafalaya River. Every day, in every season, it holds the hydraulic balance between the two channels within a narrow operational range, forcing the river to divide approximately 70% of its flow toward the Mississippi and 30% toward the Atchafalaya. In 1973, a major flood event pushed that structure near its rated capacity. Water scoured the riverbed beneath one of its primary gates, severely enough that the Corps of Engineers assessed a possible structural failure within days. At its failed, the diversion might have been irreversible. The engineers held it. The structure was reinforced and expanded in the years that followed. It has been upgraded multiple times since. Consider what that commitment actually means. The United States federal government is permanently committed to maintaining a hydraulic structure whose sole purpose is to override the natural behavior of the continent's largest river system. Not for a decade while a transition is planned, but indefinitely. The estimated annual cost of the associated flood control infrastructure runs into the hundreds of millions of dollars. The estimated economic disruption of a major structural failure runs into the trillions. Louisiana sits at the center of this commitment, and it illustrates a principle that extends far beyond one state's geography. Human infrastructure built at sufficient scale, in sufficient proximity to natural hydraulic forces, eventually reaches a point where the cost of maintenance exceeds what any rational analysis would authorize, but the cost of discontinuation is higher still. Economists call this a path dependency trap. You cannot afford to maintain it. You cannot afford to stop. What Louisiana reveals is not a regional failure. It is a preview. Coastal cities on every continent are facing versions of the same calculation. The infrastructure built to make them viable is increasingly expensive to sustain in landscapes that are increasingly hostile to the permanence those cities require. The Mississippi Delta is not an outlier. It is an early example of a problem that is still arriving. Louisiana did not fail. It succeeded at exactly what it set out to do. It extracted, it controlled, it maintained. Every tool available to human civilization was applied in sequence to the problem of making a dynamic river delta into a permanent address. Roads were built, a great city was founded, an entire industrial economy was constructed on top of compressed sediment at the edge of the Gulf of Mexico. The tools worked. For a while, what Louisiana reveals about us is something the people who built it understood, on some level, and chose to defer, our profound difficulty distinguishing between solving a problem and postponing it. The levees did not solve flooding, they deferred it. The pumps did not solve subsidence, they accelerated it. The oil revenue did not solve poverty, it postponed the need to address it. In each case, the generation that built the solution received the benefit. The cost arrived for someone else. That pattern is not unique to Louisiana. It is the defining infrastructure logic of the modern world. Imagine standing at the old river control structure on a quiet afternoon, the current visible along the concrete gates, the river pressing against the structure the way it has pressed every hour since it was built, patient and entirely indifferent to the calendar. The river remembers the path. We just keep arguing with it. If today changed how you see one thing, the next video will do it again. Subscribe and stay close.